This video will look at how to define what it means for a situation to be rare. That could mean it is unusual, that could mean it's an outlier, or maybe that happens a certain percentage of the time or less. We're going to start with the definition of outlier because this is a term that you might have heard before. I have some data here. These are quiz scores for our first quiz. I have 1, 7, 7, 8, 9, 10, 10, and 10. Informally, an outlier is a value that's well outside of the rest of the data set. So you might take a look at this one and be like, oh man, that's really, really low compared to the rest of those values. Let's see if that's actually the case. I'm going to start by calculating the 5-number summary. Reminder, the things that go into the 5-number summary, you're going to have the smallest value that shows up in your list, that's the minimum. You're going to have the first quarter mark. You're going to have the middle number, median, the third quarter mark, and the maximum. So looking at this, my smallest number is 1. My largest number is 10. I have my min and my max. Going through pairwise until I get to the center, I can see that my middle number is somewhere between an 8 and a 9. So if I'm splitting my data in half, I have 8 values. 8 split in 2 is 4 and 4. I have 4 in the upper and lower half. Between 8 and 9, my median is 8.5. Q1, this is the middle of the lower half. So if I have 4 values, halfway in that is between 7 and 7, 7. Upper half, I have halfway between 10 and 10. That gives me 10. So if I have the minimum, Q1, the median, Q3, and the maximum, I've broken my data up into 4 quarters. That's why this is called the first quartile, or Q1. It's 1/4 of the way in. And why this is called the third quartile. It's 1, 2, 3/4 of the way into the data set. I'm going to draw a visual for this. I'm going to make a box plot. So when I'm making my box plot, I start with a number line that is properly spaced so that way I can get a true feel for the shape of the distribution. And I'm going to mark all these values. My minimum is 1, that's right there. Q1 is 7, that's right here. The median is 8.5. Q3 is 10, and the maximum is also 10. When I make a box plot, I connect Q1 and Q3 to get my center box. This represents my middle 50% of the data. So I'm just going to write that above just as a note. This is the middle 50%. That's where the bulk of my information is. So if anything is really far away from this middle block, I would consider it to be rare. So for example, 10 is literally on that block. I don't think that's that far away. I don't think that's rare. But 1, look how big that tail is to that left side. That seems like this might be considered a rare value. Whenever I make a graph, I should always include units. So I'm just going to quickly add that. This was the score on the quiz. And whenever I have a graph, I should also have a title. I'm just labeling that stuff informally so you remember that that's sort of the best practice thing. Does 1 look rare to you? I would say yes. And my reason for this is it is a long distance, or really far distance, from the middle block. Outliers are defined differently depending on the source that you look at. I'm just going to go through this picture here real quick, and I'm going to move my mouse until I get to a certain point in this box where we might consider it to be an outlier. So here's what I'm going to do. I'm going to start at this point of the box, and I'm going to move my pen down until I think I'm a considerable distance away. So you might think this is a really far distance away from that block being 1 block away. And I might agree with you. In fact, some people define an outlier as being 1 block away from the middle. I'm going to keep going just a little bit more, like really pushing how much I would be comfortable with. Ooh. This is my opinion. I think this might be where something is considered an outlier. That's really, really far away. It's an uncomfortable distance away. Going in the opposite direction, I would want to have essentially the same size going out here. So I might be way up in the boons in this direction in order to be considered an outlier. For our data set, I don't know how big that would have to be. Maybe that would be something like 14.5 or 15. It'd have to be a really, really large number in order for me to consider it an outlier in the too high direction. So intuitively, what I've got going on here for trying to visualize it, I can pretty much fit in roughly 1.5 of these boxes going both down and up. I'm going to formalize this language just a bit, but it does seem like we're going 1.5 of those middle boxes both below this part and above this part of my data. So lower fence, that's what I'm going to give this thing as a technical name. Looks like it starts at the lower part of the box. That's my first quarter mark. And my lower fence goes down from there, so I subtract from there. And I'm subtracting 1.5 of those center boxes. Now the term for the box is the size of this inner quartile range. So tiny definition here. My inner quartile range. My IQR, if I'm labeling or lining that stuff up correctly. This is Q3 minus Q1. It's the range, or it's the size of the box. So if you said Q1 minus 1.5 boxes for the lower fence, some people might be confused what you meant by that word box, because the technical term for it is IQR. Upper fence. I would be worried about this value way out here coming off of this side of the box, which is Q3. Going in this direction makes it bigger, so that's adding 1.5 boxes. Intuitively, you're going 1.5 blocks above and below the middle 50%. This is Q3 plus 1.5 times the IQR. If you're in between those values, if you're inside of the fences, it is considered to not be an outlier. If you are on or outside of those fences, it is considered to be an outlier. So let's look at an example. Would 1 be an outlier? Would 10 be an outlier? Well, 10 clearly looks like it is not an outlier, but let's still find the fences. Upper fence and lower fence. So to find my upper fence, I'm going to start at Q3, and I'm going to go up 1.5 boxes. Q3 was 10, so I'm going from 10 up 1.5. My IQR is the size of this block up here, from 10 to 7. That's the width there of 3. So from 10 to 7. I'm going to type this into my calculator. 10 minus 7, I'm getting 3. 3 times 1.5, I'm getting 4.5. If I add this together, the largest something can be before it's an outlier is 14.5. Going in the opposite direction, I'm worried about it being too small compared to this edge of the box. That's Q1. But I'm still going the same size up and down, 1.5 times the size of the box. And again, you might disagree with me. You might actually think that if you were just one box away, that would be considered an outlier. If you look online, you're going to see a lot of different definitions where this number changes. I'm being consistent with the textbook that we're using for this course. They use 1.5. Q1, we start at 7. We go down 1.5, the size of that block. This is still 3. This is still 4.5 when I do that multiplication. I believe this gives me, ooh, and I did a pretty good sketch of that. Good work, me. 2.5 as that lower fence. So if you have any value that is between 2.5 and 14.5, this is not an outlier. So for example, x equals 10. That is between those two values. That would not be an outlier. But x equals 1. This is not inside that range from 2.5 to 14.5. And since it's not inside, I would consider that to be a rare quiz score. It would be an outlier. When I'm talking about this stuff and I'm looking at the 5-number summary with the minimum, Q1, median, Q3, and the maximum, this is really related to sort of the position of where it is in the list, breaking things up evenly into quarters here. So this is a position-based definition of what it means to be rare. If you're defining the center using the median, you have to use the 5-number summary to talk about the spread. If you're using the 5-number summary to talk about spread, you have to use this terminology of outlier and not an outlier to describe rare and unrare events. Let's look at a situation where we define everything based off of all of those individual values. So reminder, the other way to measure the center and spread of a data set is the sample average and the sample standard deviation. So this is going to be value-based definitions. So if I wanted a weighted average, I would add all the values 1 up to that 10 at the end, and I would divide by the number of terms. I have 8 values in the list. So I'm going to try that out here. 1 plus 7 plus 7 plus 8. I'm just adding them up. And when I did this, I got 7.75. From here, I can calculate my standard deviation. I'm just going to do the setup for this, and I would encourage you to go through this whole problem. But the variance, you take the first value in your list, 1, subtract the center, squared, plus the second value in your list, minus the center, squared, and then you're adding all those things up. And on the denominator, you have the number of values minus 1, so 8 minus 1. When I did this, and I could have done it wrong, because there's a little bit of round off error sometimes associated with this, I got a variance of about 9.066. If I want my standard deviation, that's the square root of that number. And this is giving me something of about 3.011. When I'm dealing with these values, this is what's going on. The average you should think about as representing the middle of a number line where you can think about displaying your graph. So 7.75, that's sort of my weighted average of what's going on with my graph. If I wanted to know what I should count by instead of counting by ones, so I'm a bit more consistent, counting by 3.011, my standard deviation, might give me a better picture of what's going on. So let's do that. I have 7.75 plus 3.011. This gives me 10.761 here. I'm going to add 3.011 again, 13.772. In the opposite direction, I'm starting at the center, and I'm going to be subtracting standard deviation. So on this side, I'm adding standard deviations. On this side, I'm subtracting them. $4.739, I'm going to subtract again. $1.728. And I can see that I'm counting by a considerably larger number this time, and I'm covering my whole data set much, much faster. If I'm trying to figure out what I consider rare on this set, within one standard deviation, I still have almost all of my data. That doesn't seem like it's very long distance away, but perhaps 2 tick marks away might be considered rare. So I'm going to just mark these things here and here. And I would say anything within 2 standard deviations of the center is considered to be usual. So from the middle, from this average x bar, if I go up and down 2 tick marks, like here to here, this area of my graph is considered usual. Anything that is bigger than this is unusual, and anything smaller than this is also unusual. So would we consider x equals 1 to be usual or unusual? Well, let's see where that is on my graph. So let's do the math here using this formula where I have average plus or minus 2 times the standard deviation. So my interval for what I consider usual to be, I'm going to go from the center, 7.75, and I'm going to add and subtract 2 times that standard deviation. So doing this with the subtraction, I get a low value, 7.75 minus 2 times 3.011 of 1.728. Oh, I can even see that in my picture. A little bit weird that I retyped that in my calculator, but that's okay. And for a penny and for a pound, I'm going to type it in with a plus sign. And on the high side, I'm getting 13.772. So anything inside of this is considered usual. Anything outside of this is unusual. Looking at 1. 1 is smaller. It's not inside of this interval. So this would tell me x equals 1 is unusual. And in contrast, 10 is inside of this. So x equals 10 is usual. Looking at another example, suppose we're looking at average heights. The average height of individuals is 68 inches tall with a standard deviation of 3 inches. Would it be uncommon to run into someone that's 76 inches tall? Well, let's check. Interval for usual from the center, 68. I'm going to go up and down 2 standard deviations. 2 times 3 is 6, so I'm adding and subtracting 6. On the low end, I will get 66 inches. Ooh, not 66. 68 minus 6, 62 inches. And on the high end, I have 68 plus 6. I get 74 inches. So looking at 76, that is larger than the highest value. This is not inside of this interval. I would say x equals 76 inches is unusual. In particular, it is more than 2 standard deviations from the center. How many standard deviations away was it? Well, I don't know. I just know that it's more than 2. Let's draw the picture out. If you're better with the picture, try doing it from the picture. The middle is 68. And I'm adding and subtracting 3. That's the value I'm counting by. That's my standard deviation. 68 plus 3 gives me 71. Plus 3 again gives me 74. That's where that high value is coming from. 68 take away 3 gives me 65. Take away 3 again, I have 62 as the low. Now, anything inside of this area is considered to be usual, and anything outside of it is unusual. $76, well, let's just keep counting. So 1 standard deviation, 2 standard deviations. If I add another 3, 3 standard deviations is here at 77. 76 is here. It is more than 1, 2 tick marks away, but it's not quite 3 tick marks away. So if I want to know how many standard deviations this thing was away in total, I might want to know what is the total distance from 76 to 68. So how far away from the center am I? And how many of these 3 gaps can I fit in? So I'm just brainstorming a little bit, and I could be wrong on this. But number of standard deviations from 76 to 68, I was 8 units away. 8 units away, but it matters by what I'm counting by, and it looks like I am counting by or divided by 3. So let's take that gap size of 8. I'm going to divide that by the thing I'm counting by 3. And in my calculator, I get 2.66 repeating or so. Let's see if that looks reasonable on my picture. 1, 2, 2/3 of that last jump away, 2.66 repeating. That's more than 2 standard deviations. So technical term, we call the number of standard deviations a value is away from a center a z-score. The way we calculate a z-score is we take the value, in this case 76, the value that we're trying to see if it's usual or unusual. We subtract the center of the graph, the basis of this interval, and I divide it by the thing I'm counting by. Throughout the term, we're going to be calculating a lot of different z-scores. And you might see a bunch of different formulas for them, but they really just come back to this. So I would encourage you to only remember this general setup for a z-score as being the value minus the center divided by the standard deviation. Calculate the z-score for 76 inches, okay? My value is 76. My center was 68. My standard deviation was 3. So I have on the top the gap size, and on the bottom I have the thing I'm counting by, my standard deviation. When I do this, I get 2.66 repeating. We consider this to be unusual. Now I can define usual and unusual based off of the z-scores. And I would like you to take a moment and see if you can figure that out. What would it mean to be usual for the z-scores? What would it mean to be unusual? Okay, so revisiting this idea of usual and unusual for z-scores. If something is within 2 standard deviations, so if you have a z-score between -2 and +2, that's the number of tick marks you are away from the center. Labeling it on this picture. The center of your graph is a z-score of 0. It is no tick marks away. 1 tick mark away is a z-score of 1. 1 tick mark away but down is a z-score of -1. Up 2 tick marks, +2. Down 2 tick marks, -2. So having a z-score between negative and +2 inside of this interval here is a compact definition for what it means to be usual. Let's keep that in mind when we look at this next example. The average number of times a coin shows up, or proportion of times is probably the better phrase here for this. That you should get heads after 100 flips is 50% of the time. This is pretty reasonable. So this tells me that if I flip a coin a whole bunch of times, on average, I expect to get 50%. Now, I'm not always going to get 50%. I might get like 51 or 49%. In fact, the amount that this varies by is 5%. So I'm going to count by 5% on my graph here. 1 tick mark above and below, counting by 5%. 2 tick marks above and below, anywhere from 40 to 60%. Would it be unusual to get heads 78% of the time? Yeah, by a lot, right? So within 2 standard deviations, my usual number of times that I should get heads is anywhere from 40% of the time to 60% of the time. This is actually a true fact. If you flip a coin 100 times, I would anticipate, usually about 95% of the time, people will get between 40% heads and 60% heads. So let's say someone ended up getting heads 78. Would you be surprised by that? Well, let's check. Let's find the z-score. We're going to take their value. We're going to subtract our average or our center from that. And we're going to divide this by what we're counting by our standard deviation. So the value is 78%. Our center is 50%. And we are counting by 5%. We're calculating the z-score. Because just looking at my sketch, 78 seems like it'd be a really far distance away from that center. It might be kind of hard to draw this. When I typed this in, I ended up getting 5.6 for my z-score. Since it is more than 2 standard deviations away from the center by a lot, %78 is considered unusual. In fact, that's such a high number that if I saw someone get 78% of the time heads for 100 coin flips, I might have some evidence that they're cheating at that point. In general, if a value is unusual, that tells you that there might be something going on. Either they're really lucky or they could be cheating. So this was a way to find rarity using weighted values. But looking at this was number-based data. So reminder, that's called quantitative data. Looking at our outlier definition, this is also quantitative data. So a question might arise, how do I define rare if it's qualitative or categorical? So let's look at a way to look at the likelihood of events if I have word-based data. And I'm going to display things here using something called a contingency table. So when we don't have centers and standard deviations to rely on, we try to make grids to see what's happening. So make a table to explain what's going on if there are 100 animals with 60 dogs. The rest of them we'll consider to be non-dog. 70 are short-haired. The rest we'll consider to be not short hair. And 40 are short-haired dogs. When I'm creating these grids, I'm going to put one of the categories, for example, cat and dog, as columns. Columns are like columns of buildings. Columns go up and down. I'm going to put my other category, in this case, short hair, long hair, as the rows. Rows are like if you row a boat, you row a boat side to side. Now, what I've done when I've created this grid is I now have all the combinations. For example, I have short-haired cats. I have short-haired dogs. I have long-haired cats. I have long-haired dogs. On the outside, I like to add 2 lines here to help me determine sort of the difference between inside and outside. It kind of looks like equal signs, big equal signs. I'm going to put the totals for those categories. So just practicing reading these new values, this is the total number of cats, the total number of dogs, the total number of short-haired animals, the total number of long-haired animals, and the total number of animals altogether. I'm going to fill in these totals, and then I'm going to solve for the remaining values. So let's see what we're told. 100 animals. That's the total of all of the animals. So I'm going to put that in the lower right corner. Of these, 60 in total are dogs. So total for dogs, 60. Already I can solve for one missing piece of information. If this area only had cats and dogs, and 60 of them were dogs, then the remaining amount, 40, must be cats. Let's keep going. It says 70 animals are short-haired. So the total for short hair is 70. This is a lot like a Venn diagram if you've seen Venn diagrams before. 70 and something gives me 100. 70 plus 30 gives me 100. So everything should add up correctly horizontally and vertically. 40 are short-haired and dog. So this is a combination of events. And all of your combinations are going to be on the inside. So I'm looking for short-haired meets dog. I got 40. I'm going to make sure everything adds up. 40 plus what gives me 60? Well, 40 plus 20 gives me 60. 40 plus what gives me 70? Well, 40 plus 30 gives me 70. 30 plus what gives me 40? 30 plus 10 gives me 40. And the great part of these is when you put in this last number, it should work both vertically and horizontally. So let's double check. 10 plus 20 gives me 30. That looks great. Everything is adding up the way that it should. So out of all the animals, what percent are dog? So out of all animals, looking at my table, the total number of all the animals is 100. How many of those are dogs? Well, the total for dogs is 60. So I can see that 60% of those animals are dogs. If it's out of 100, these are all percentages, so I can actually answer some other questions as well. So if you ask me, what percentage of animals are long-haired cats? I would say 10% are long-haired cats. 30% are short-haired cats. I have a decent understanding of every possible combination that can happen, and this table gives me a way to visualize that. Let's do another example of a table. Mr. Wary has 60 plants in his garden. 40 of these things I grew from seed. 20 of them came from Al's garden center. Suppose that 15 of the plants that I'm growing are vegetables and the rest are not vegetables. And that 10 of those vegetables happen to be from Al's garden center. Create a contingency with this table with this information. Let's try. I'm making these as 2x2 grids because I only really have 2 things in each of these categories. But if I had something like vegetables and annuals and perennials or something like that, I could have more than 2 things in a column or more than 2 things in a row. I'm just starting out with small tables, get used to them before going up to something bigger. I would like you to pause the video and try to fill in this table to the best of your ability. One set of variables, and that variable set is usually that thing like A and not A. Second variable, B and not B. If you're trying to put combinations of things like Al's vegetables as a column, that's not how that works. Al's vegetable should be a spot where vegetable meets Al's. So be really careful when you're setting these things up. Pause the video, try it out. Let's see what you can come up with. Okay. I'm hoping you paused it. I'm hoping you tried it. Okay, if you didn't, but let's see. 40 from seed, 20 from Al's. So I have things from seed and I have things from Al's. In total, 40 from seed, 20 from Al's, and out of 60 plants in total. One of my variables is the location of where I'm getting the thing. The other variable is being vegetable and not vegetable. "15 of the plants in total are vegetables." You might have the same things, but as mirror image. So you might have put seed and Al and vegetable, non-vegetable, just switching your rows and columns. That's okay. You should still end up with the same final answers, just in a different order. If 15 are vegetables, that tells me the rest being 45 of these things, are not vegetables. Suppose that 10 of the vegetables were from Al's. So vegetables meets Al's 10. And I like these. These remind me of Sudoku. These are just little brain teaser puzzles at this point. I just have to make sure that everything adds up correctly. Something in 10 gives me 15. 5 and 10 gives me 15. 5 and 35 give me 40. 10 and something gives me 20. I'm pretty sure 10 and 10 gives me 20. Double checking, 35 plus 10 gives me 45. This is looking pretty good. Now let's answer some follow-up questions based off these tables. Out of all plants. So when I'm setting up these percentages, whatever it is out of goes on the bottom. So out of all plants, this is out of 60 things in total. How many of them were vegetables? Well, 15 out of the entire 60 were vegetables. I'm going to type this into a calculator, and I'll see what I get. I get 0.25, or 25% of the plants are considered to be vegetables. Out of the plants from Al's. So if I'm looking at my table, this is telling me that I am only in this column here for Al's. Inside of that, this is out of a total of 20. What proportion of these 20 are vegetables, while 10 are vegetables out of the 20? That gives me 0.50 or 50%. I'm noticing something already. If I just look at my garden in general, 25% of my garden is vegetables. But if I look at the plants that I bought from owls, there's a considerably higher percentage of those things that happen to be vegetables. In other words, I am more likely to get my vegetables from owls. In other words, there's a relationship between the variables of location and being a veggie or not a veggie. Out of all the plants not from owls. So in other words, this is out of everything from seed. What percent are vegetable? Okay. Out of seed, that's this part of the table. You can even box it if it makes it easier for you. In total, 40 things were from seeds, and only 5 out of the 40 were vegetables. So 5 divided by 40, this gives me 0.125 or 12.5%. So comparing these, 50% of my things from owls are vegetables, but only 12.5% of my seed things are vegetables. So I am less likely to get my vegetables from seed. So again, this is telling me that there's a relationship between these variables. The statsy way of saying this is independent and dependent. We say two events are independent if the outcome of one event does not impact the outcome of another event. So independent, which I usually abbreviate as IND, this means that there is no relationship between the variables. Having red hair and having a calculator. Having red hair does not impact the likelihood that you have or do not have a calculator. There's no relationship. They do not affect each other. If things are related, DEP for dependent, then there's some sort of a relationship between them. They affect each other. So for example, if my probability changes for different subgroups, it is dependent. And if it stays the same, it's independent. Let's look at this. 25, 50, 12.5. My ratios change. My two events, there is a relationship. And because there is a relationship, this tells me the events are dependent. If you're wondering what it would look like if it's independent, I'm just going to write that to the side here as a what if. If it happened to be independent, you might see something like this, where 25% of all of the vegetables in my garden were came from the plants. 25% of things from owls are vegetables, and 25% from seed are vegetables. So when it's independent, you are going to notice that it has the same ratio throughout. If your numbers are changing for the different subgroups, 25, 50, 12.5, if you have a different ratio for your different subgroups, then this tells you that they are dependent. This is a skill that you will practice a lot in your homework and as we're going through more problems together. But I just wanted to give you an early exposure to it so you can have an idea of what's going on. Let's do another one. So to save on a little bit of writing, I'm inventing a new notation. Probability of A, vertical line B. This is read as the probability of A given, that's what this vertical line means, given B. When you're dealing with something like this, B is your denominator for your fractions that you're setting up. It's telling you the part of the table that it is out of. So going back and relabeling some things, not from owls. So this was the probability that something was a vegetable if it was out of something that I grew from a seed. From owls. So this is out of, or I divided by owls. Whatever your denominator is, that shows up as the second part of the set. Owls, and I'm wondering how much is from vegetable. This one was out of all the plants, so I don't say a special denominator at all. I would just say percentage of things that are vegetables. So let's take a look at another problem. I'm going to give you this setup. I'm going to pause the video. I'm going to ask that you pause the video as well. A total of 680 PCC students were surveyed. Of those, 292 polled were from Cascade. The rest were from Sylvania. 354 of them had healthcare. The rest did not. 136 had healthcare and happened to be from the Cascade campus. Create a table with this information, and then try to find the probability of having healthcare if you are from Sylvania. Find the probability of healthcare if you are from Cascade, and try to figure out if there's a relationship between location where students take classes and having and not having healthcare. Again, please pause the video and try this out on your own. Okay, let's see how you set that table up. So I am looking at two different campuses, Cascade and Sylvania. Now, if I had 4 campuses and I wanted to set this up as like Cascade, Sylvania, Rock Creek, and Southeast, I can set this up for more than 2 columns. But this is another problem that only has 2 variables, or 2 states for each of the variables, Cascade, CA, and Sylvania, SY. Now, I also have healthcare. I'm going to abbreviate that as HC, and no healthcare. And on the outside, I'm putting my totals. In total, they sampled 680 students, so I'm going to put that in the lower right-hand corner. 292 were from Cascade, so for the total for Cascade, I'm going to put 292. The rest were from Sylvania. Okay, great, I can solve that. 354 in total had healthcare. 354 had healthcare. The rest did not. 136 had healthcare and were from Cascade. So this is going to be where healthcare meets Cascade. Healthcare meets Cascade, 136. I'm going to find the rest of these numbers just by doing some subtraction. So I have 354 minus 136. That tells me that this number right here is 218. I have 292 minus 136. That gives me this number right here is 156. Let's find this number. I have 680 minus 292. Got 388 sitting there. Let's find this number. I have 680, take away 354, I have 326. And finally, this number. I have 388, take away 218, that gives me 170. Quick check, 156 plus 170 gives me 326. This is looking pretty good. Okay. Calculate the probability that someone has health care given or out of the fact they're from Slovenia. So the second number here, this is what I know about them. So in my table, I am only going to be using the information in the Slovenia block. The denominator is 388. Do you see how this kind of looks like a division symbol? It doesn't hurt to think of it like that. This is dividing by Slovenia. Inside of this block that I'm not allowed to leave now, I'm wondering how much healthcare there is. And I see that there's 218. I'm going to type this into a calculator and see what I get as a decimal, and I'll rewrite that decimal as a percentage. I get 0.562 or so, or 56.2% of people from Slovenia have healthcare. Let's look at Cascade. Out of Cascade, so I'm dividing by Cascade now, and that's this first column. This was out of 292 people. I'm not allowed to leave Cascade when I'm answering this question. It's telling me my universe. And inside of this 292, the amount of healthcare that exists is 136. I'm doing 136 divided by 292. That gives me a percentage of 46.6%. Are the events of healthcare and campus independent? Well, reminder, independent means that they have the same percentage or the same ratio. So independent would mean that the probability of A is the same as the probability of A for some subgroup B would be the same as the probability of A given that you are not in the subgroup B. In other words, independent means that the ratio stays the same. But I see a problem here, or not a problem as much as just a discovery. 46% of students from Cascade have healthcare, 56% from Slovenia do. So there is a relationship. And since the ratios are different, the events are dependent. And we could be even more specific because dependent just says there's a relationship. We should try to figure out what that relationship is. In this case, if you are from Slovenia, it looks like the chance of having healthcare is higher than if you're from Cascade. So you are more likely to have healthcare at Slovenia. And really that second part is the crux of doing a project at all. We were able to, by doing this research, to figure out that different campuses had different access to services. So this could show some sort of an inequity that exists within our student population. As a final note with this notation, be careful with the ordering. So if I see Cascade vertical line health, this means out of health. So if I'm setting this up, this would be for the people with healthcare. This is out of 354. From those 354, 136 were from Cascade. If I type this into my calculator, that gives me 38.4%. Now, if I'm writing out what the sentence is telling me, of those with healthcare, 38.4% are from Cascade. If I wrote out this earlier sentence, of those from Cascade, 46.6% have healthcare. So when you switch the order of these things, you change the piece of information that's given. For example, if you know things about a deck of cards, there are hearts and diamonds are two of the red suits. Clubs and spades are two of the black suits. So if I asked you, what's the probability that something is a diamond, considering it was red? Half of the red cards are diamonds. If I asked you, what's the probability that something is red, given that it's a diamond? Well, 100% of those cards would be diamonds, would be red. So if you switch that given statement, you're changing the sentence structure. I'm going to try to avoid doing as much card examples as possible because I know not everyone has seen what a fair deck of cards looks like. So I'm going to try to stick to more concrete stuff like that. But just in case you have some experience with that, I thought I would throw out that example. Finally, just building up this toolbox to get some more language. In stats, if I say the word and is restrictive. So for example, if I say I want candy that's both red and sour, I want it to have both of those things. It has to be red and sour at the same time. If I said I want candy that's red or sour, that means I'm happy with anything that's red or I'm happy with anything that's sour. If it happens to be both, cool. So and is restrictive or gives you more when it comes to options. So I'm going to create another table, and then I'm going to practice the difference between or, and givens, and look at another thing with independence. It brings it all together. Survey of PCC students, 49% had a car. So it looks like I have car and no car. And then on the outside, I'll have total. Some students were from Cascade, and some were from Sylvania. And on the outside, I have my totals. It doesn't give me a total for percentages, but percentages always add up to 100%. So let's put 100% in that lower right-hand corner. 49% had a car as their primary means of transportation. So that must mean the remainder, 51%, did not have a car. 44% were from Cascade. So that remains the remaining 56% were from Sylvania. 19% car and Cascade, 19%. Then let's do addition and subtraction to find the rest. 19 and 30 gives me 49. 19 and 25 gives me 44. 25 and 26 gives me 51. 30 and 26 gives me 56. Okay. Probability of Sylvania or car. This means I am happy with this or with this, with either Sylvania is a success, and car, this is also a success. So let's highlight those spots on the inside of the table and add them up. These people were not from Sylvania, but they had a car, so I like them as part of this total group here. These people are not from Sylvania. They do not have a car. I'm not including them as part of this total. These people are from Sylvania. That was the first thing I was looking for. That's a success. They also have a car. Cool, they've got both things I'm looking for in this case. These people are from Sylvania. They don't have a car, but that's okay. Either one of these things is considered a success. In general, when you're looking at OR, you're going to see that you end up with all the spots for one thing and all the spots for another thing. You're adding up a lot of options. In this case, adding up these numbers, 19% plus 30% plus 26% tells me that 75% of the people sampled were either from Sylvania or had a car. Another way to do this, do you notice how it was everything but this 25? 100% take away the 25% would give me 75. And where OR was all of these spots, and is only going to be the spot where the two things overlap, where they meet. So Sylvania and car is only this one block that I got here. That's this number of 30%. Percentage of car. Well, this one's fast. It even tells me in the paragraph, percentage of people that have a car is 49%. Percentage of people from Sylvania that have a car, percentage of people from Sylvania that do not have a car. Percentage of people from Sylvania that have a car, percentage of people from Sylvania that do not have a car. Is that really what I'm looking at? What am I looking at here? Let's look at the second thing and highlight it, because if you go into autopilot mode, it's really easy to get these things wrong. So what I like to do is circle that second thing, and this is my given piece of information. So this tells me that this is out of those people with a car, and I'm finding out what percent are from Sylvania. So let's look at the grid. Out of car. So this is out of that 49%. And inside of this, 30% are from Sylvania. So I've got 30 out of 49%. This gives me 61.2% of those people with a car happen to be from Sylvania. Let's look at the non-car people, and let's figure out how well Sylvania is represented in the group without a car. No car is the second column. Inside of the second column, my total that I'm working with is 51%. The amount of those people without a car that are from Sylvania is 26. 26 out of the 51. This is giving me 50.98 rounded. I rounded that up to 51%. Let's compare. If people have a car, there's a 61.2% chance they're from Sylvania. If they do not have a car, there's a 51% chance that they're from Sylvania. So I might be curious, is there a relationship between having a car and where you take your classes? In this case, it looks like if you have a car, you are more likely to be from Sylvania. So it looks like there's a relationship between these variables. And if there's a relationship, this is telling me that the events appear to be dependent. This lesson had a lot of vocab. You learned some new skills with making tables. You learned the difference between independent and dependent. There's going to be some stuff to practice here. I continue to recommend that you try to go through as much vocab as possible, thinking of this kind of like learning a new language. But we will practice these skills together as well through the upcoming videos.